This is a little review of precipitation reactions, abbreviated PPT, RxN, precipitation reactions. They're a double replacement reaction that forms a solid. If both products are soluble, then the reaction does not occur. In order to check if something's soluble, you look at the solubility rules. There are three different ways to represent a precipitation reaction. One of them is through a molecular equation. And the molecular equation shows the overall reaction, but it doesn't necessarily show the forms that the reactants and products are in. A complete ionic equation represents all products and reactants that dissolve as ions. And then the net ionic equation, which represents only the components in the reaction that change. Let's take a look at an example of these three. An example, this is probably the most extensive example that you're going to see. You're going to have to write your own equations. We've got a solution of potassium hydroxide, and it's mixed with a solution of iron 3 nitrate. So what we want to decide is what happens. Well, we're going to start by writing the equations for our reactants. We've got potassium hydroxide. If you're a little shaky, you may want to go to your list of common ions. Potassium is a positive 1 right there, and hydroxide down here is a negative 1. So it's just going to be KOH. And since that's in solution, we should write down that it's aqueous. And that is mixed with iron 3 hydroxide. Again, that's also aqueous. So now what we're going to do is we're going to take a look at this, and we see that it's a double replacement reaction. I've got two ionic compounds, ionic compound, ionic compound. So our ions are going to switch places. The potassium is going to combine with the hydroxide, and the iron, oops, that should be iron 3 nitrate, rats. There we go. I knew that looked funny. All right, there we go. The potassium is going to combine with the nitrate, the positive here and the negative there, and the iron 3 is going to combine with the hydroxide, again, the positive and the negative ion. So what we're going to form is potassium nitrate and iron 3 hydroxide. Now, we need to decide whether this reaction actually occurs by checking the solubility of these two products. If both of them are soluble, they both dissolve, and we get like a collection of ions in the beaker, and nothing really happens. If one of them is a solid, then we have a reaction. So in order to decide if things are soluble, what we do is we check the solubility rules. We'll try potassium nitrate first. Again, we apply these rules in order. Nitrate salts are soluble. What that means is, well, potassium nitrate must be soluble, so we're done. This guy is aqueous. He dissolves. Now to check for iron 3 hydroxide. Nitrates are soluble. It's not a nitrate. Salts of sodium, potassium, ammonium are soluble. That's not the case either. Chloride salts, it's not a chloride salt. Sulfate salts, it's not a sulfate salt. Here we go. Most hydroxide compounds are only slightly soluble. We've already said that slightly soluble really means the same thing. Insoluble and slightly soluble are the same thing. Slightly soluble equals not soluble. So there's our culprit. The iron 3 hydroxide is not going to dissolve, so this will be a solid. Everything's good here except for we need to balance this. I've got a potassium here, I've got a potassium there. I've got 3 nitrates. Well, let's do this. I've got a hydroxide here. I've got 3 hydroxides here, so that means I need to put a 3 in front of this. Well, now that gives me 3 potassiums, so I go over here and put a 3 there. I had 3 nitrates here. I now have 3 nitrates, NO3 here. Everything's good. It's now balanced. So now what I can do is move on and write my complete ionic. Again, this was my molecular equation. It describes what's going on, but again, it may or may not have the states. In this case, I put in the states. For the net ionic equation, what we do is we take anything that dissolves and we break it into its ions. So, potassium hydroxide is aqueous, so we will break that into its potassium ions and its hydroxide ions. Again, those guys are both aqueous because they dissolved. Iron 3 nitrate is aqueous, so that will dissolve. 3 plus, because it's iron 3, Roman numeral 3. Other way to check this is nitrate is a negative 3, and I've got 3 of them, so that iron must be a positive 3. NO3 minus. Again, both of these guys are aqueous. We'll discuss balancing in a few minutes. Potassium nitrate, again, dissolves, so it's aqueous. So we've got potassium in its plus and nitrate with its minus. Aqueous, aqueous. And then last we come to the iron 3 hydroxide, which is a solid, so that doesn't dissolve, so we do not write it as its ions. It stays as iron 3 hydroxide. Now as far as balancing goes, a couple ways to do this. I could use the fact that I balanced this before up here and just drag down my coefficients. This potassium hydroxide, when it breaks up, it'll form, since there's 3 of them, it'll form 3 potassium ions, 3 hydroxide ions. The other way I can look at this is I can just do it like I normally would. I've got a hydroxide here, but I've got 3 hydroxides here, so I'm going to need a 3 in front of that. What else? Oh, over here, iron 3 nitrate, that guy is going to break up into 3 nitrates, 1 iron, so that gives me 3 nitrates over here, so that gives me I need 3 nitrates over there. It's really easiest to use the molecular equation. Again, this broke up into 3 potassium ions, 3 hydroxide ions. This breaks up into 1 iron ion, 3 nitrate ions. This breaks up into 3 potassium ions, 3 nitrate ions, which I already covered, and then this stays the same. Balanced, it is. So that's my net ionic equation. The last one is the net. Oh, that's not the net ionic equation. Why did I mislabel that? That is my complete ionic equation. Sorry about that. Alright, here we go. Now we're getting to the net ionic equation. The net ionic equation, we said, only shows what changes What we can do with the complete ionic equation is get rid of the things that are spectator ions. Spectator ions are the same on the product, start with reactant, the reactant and product side. So things that are spectators would be stuff like potassium. I've got 3 potassiums over here. I got 3 potassiums over there. Same on both sides. This guy is a spectator. Hydroxides. I've got 3 hydroxides over here, but I don't have anything that's written as 3OH minus on this side, so that guy's not a spectator. Fe3 plus, I don't have an Fe3 plus on this side. That guy's not a spectator. 3NO3 minus, 3NO3 minus, same on both sides. Those guys are spectators. So these guys are spectator ions. Spectator, 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 spectator. We take what's left and make our net ionic equation. So what I'm left with is Fe3 plus, usually write the positive ion first, although it doesn't really matter, and that's aqueous. And that will combine with my 3 hydroxides. Those guys are also aqueous to produce. The only thing left on this side is my iron 3 hydroxide, FeOH3, as a solid. So that is my net ionic equation. So those are the 3 different ways to represent a double replacement or precipitate reaction, a double replacement reaction that forms a solid. Hopefully this helps for tomorrow's quiz.